Okay, Bismillah. So we continue our lecture with chapter 5.5, which is the general equations. So yeah, in this slide, we will learn the general energy equations. So as mentioned many times before, according to the first law of thermodynamics, which is also applies to the conservation of energy principle, energy neither can be created nor destroyed. Similarly, like the transfer of mass in a control volume, the difference between the energy that enters and exits a control volume equals to the difference of energy in the control volume of the system. So we have in and out. So it's the difference between these two is equals to the rate of change of energy in the control volume or in the system. So it can also be written as the net heat transfer in and the net work. So the difference, the total, which is the net, is equals to the rate of change of energy in the system. The net here is basically the difference of in and out. So it can be either positive or negative, this Q net and the W net. So it depends. So if they are positive, that means that the rate of change of energy in the system is increasing. If the total are negative, that means the rate of change of energy in the system is decreasing. Where the net heat transfer and work rate is difference between the one supplied and accepted from the system. E here is the total energy per unit mass. So notice the lowercase of this E. If you have a capital E, this is energy. But if you have a lowercase for all of these like U, KE, and PE, here if you notice, we use lowercase. So that means that it is per unit mass. So the one that we have here, like this is a capital KE and PE, it is like basically the energy. It's not per unit mass. If you have like, for example, like PE, usually we have a unit of kilojoule per kilogram. So that's the difference between lowercase and capital case. Here in this slide, it discusses the energy transfer by heat. The thermal energy is the sensible and latent forms of internal energy, where heat transfer is the transfer of energy from one system to another as a result of a temperature difference. So the direction of the heat transfer is always from the higher to lower temperature. So if you notice in this figure, so here in the first one, you can see that no heat transfer is because due to the same temperature. So it is already homogeneous. So no heat will be transferred because none of them is lower or higher than the other. For the middle one, as the temperature is colder, so in this when the temperature is lower than the room, so there will be a heat because as is mentioned here, the heat will be transferred from the higher temperature to lower temperature regions. And as we notice that, here we can see that the heat transfer is bigger compared to the one in the middle. It is because this is much colder compared to the one on the third. It's much colder than the second one. So if you notice, there is a condensation happen on the surface of the body. It is if one body is too cold in a very humid place, the humidity in the air will be condensed. The humidity, which is the water, the vapor, will be condensed on the cold surface. That is like why usually if you wear eyeglass, you sit in a car with a very cold air conditioning system, and when you leave the car in the hot sunny afternoon, you can notice that there is a condensation happens on your eyeglass. It is because the eyeglass remains cool at the moment you exit the car, and due to the high humidity in the climate, condensations happens where the vapor in the air becomes liquid on the surface of your lens. So that's basically why I have the condensation, because it is very cold relative to the temperature in the rooms, and due to the humidity it becomes condensed. There's water on the surface of the cold object. An adiabatic process is a process where there is no heat transfer, as you can see from the first one, and heat transfer is the time rate of the heat transfer. Okay, here we have several types of energy transfer by work. We have work, which is the energy transfer associated with a force acting to a distance, where work equals to force times area. And we have power, is the rate of work or work over time. So power is work divided by time. So there are several types of power, car engines, gas turbines. They all produce work. Compressor, pumps, fans, and mixers, they all consume work. They have several types. So you need to know which applications produce work and which applications consume work. And in this topic, we are going to total up all of the works, like the work due to the shaft, which is the one that's transmitted by a rotating shaft, or the work due to the pressure, which is due to the pressure forces on the control surface, work due to the viscous, which is the work done by the normal and shear components of viscous force on the control surface, and the other, such as this is the external work due to electric, magnetic, and surface tensions. This slide shows the relationship between shaft work and torque. For us, for this syllabus, you don't have to go too deep into this because it is not really in that fluid mechanics. So this shows the derivations of the overall work done by pressure forces onto a system. It starts from the summation of all forces comes from the pressure onto body by using this. Basically, we know that F equals to pressure times area. So just total up all the forces acting on the surface due to the pressure by using this equation, F equals to P times A. And the rest is similar to the all of the equations that we already derived prior to this. This is applying Reynolds transport theorems, which explains the conservation of energy by using the equations where the rate of change of energy transferred is equals to the rate of energy that enters the control volume and the rate of energy that goes out from the control volumes. It is similar to the mass, conservation of mass, as we know that by replacing B here, where this is the generic equations of the Reynolds transport theorems. And before this, we already used these equations for the conservations of mass, where we just substitute B here with mass. And this lowercase b is mass per unit mass, or usually 1. If we this with mass, it becomes mass over mass equals 1. But this is where we, instead of substituting mass into this B, we substitute E, energy. And this equation, if you notice, it is very similar to the one that we use for the conservation of mass, where the rate of change of energy in the system is equals to the rate of energy change in the control volumes plus this is the rate of energy that enters and leaves. And usually in our case, we just assume it's steady state where the rate of change of energy in the system doesn't change with time. We will only have these two terms. So in a typical engineering problem, they may consist of several inlets and outlets, and the total of rate of energy in both directions, which is the one is coming in and the one is going out, will be calculated. And energy also may transfer to heat and shaft work. From this equation, you can see that this is the total of energy that's leaving the control volume to the control surface, and this is the rate of energy that's entering the control volume to the control surface, and this is the rate of energy and it's changing in the control volumes. And this is all the external energy due to the heat, due to the work, and this is basically is the Q out minus Q in and W out minus W in. Basically this the general equation, but this is not yet the simplified version, so you don't really have to memorize this kind of questions. Don't stress your brain by memorizing this form of equations. We have a more simplified versions of equations which we are going to discuss in the next couple of slides. In this subtopic, we will apply what we have learned prior to this slide, where we need to find the net rate of energy transfer to a control volume by heat and work during steady flow. So if there is no heat and shaft work, we will actually get the energy conservations in the flow equations back. So see, the difference between this and the one that we already learned before, we are adding these terms. These are all due to the additional heat or work provided into the flow. So if we notice, this is the conservation of energy that we have discussed in the beginning of chapter 5. And so this is all when we take into account all of the other energy sources as well into the system. This slide shows the difference between an ideal flow with the real flow, where in ideal flow we consider there's no energy loss, hence say that the Q net is equal to the U after minus the U for. So however, in the real flow we need to consider the mechanical energy loss, so this will be added into the U which is after. Okay, like the one and on the left is the before and the one on the right is after the process. So usually what happens in the after, we expect there will be a mechanical energy loss. So whatever that is extracting the energy, we will put it on the right. So whatever that is, this is the initial energy, total energy, we put it on the left, and when we have that the energy that is being supplied into the flow, we put on the left as well. So we put whatever that cause the energy in the flow to increase, we put on the left, plus together with the initial energies, and the after energy, the energy that is after the process, we put on the right, together with all the whatever that extract the energy. So like for example here, this is the generic equations that you need to memorize. And this is the energy equations. So this is all the energies in the flow before it goes through this process, and then we have pump that is adding energy or work into the fluid, and then this is the energy that's after, the total energy of the fluid after the process, and this is the process where the energy is being extracted away from the flow, and the mechanical energy that is lost. So the summation of this on the right and the one on the left should be the same. And this is the power, whereas you know that to calculate power we need to multiply with the mass flow rate. So whenever we try to solve the power problem, we need to find the mass flow rates first, and then you just multiply the equations in the energy equations, which is we learn it at the very beginning of this chapter. Just multiply with the mass flow rates, we will get the power. Okay, this is an example of typical power plant that has numerous number of pipes, elbows, valves, and turbines. So a lot of losses can be expected here, which is due to the frictions in the pipes, head loss due to the obstructions like elbows, like sudden expansions, and etc. And also due to the inefficiency of turbines and pumps. So there will be a lot of energy or a lot of irreversible losses happen during these transformations of energy from one form to another form. This slide shows the energy equations in terms of heats. You have seen these actually equations. You have seen these equations, but this is only like in the different terms. So instead, before we describe the energy equations in terms of energy, here we discuss in terms of heats. It's just by dividing all of the terms with gravity, with gravitational acceleration g. By doing so, we will get all of these terms in terms of length. Okay, so why it is in terms of length? It is when we use, like for example, manometer to measure the pressure at each of the point. Actually, we will get it in terms of the height. This is the height of the manometer, that if you use manometer to measure the pump at several points in the pipe, so you don't really have to convert it anymore. You can, whatever height that you get, that is the H, the heat. So where we have this all like H pump, basically all the same things before. This, the H pump is the one that is provided or delivered to the fluid by the pump, and the H turbine is the one that is being extracted from the fluid and to produce shaft work. And this, the head loss, is due to the frictions and the obstructions in the pipe system, the piping system. This visualizes the conservation of energy. So on the left, we can see there are energies that entering the control volume. So it can be from the fluid itself, and also from the one is being provided into the fluid, like pump or fan, where we add more energy into the flow. And on the right, where we have the energies that is leaving the control volumes, is can be from the mechanical fluid itself and from the turbine that is being extracted away from the control volumes, and also this is the loss. This is the loss due to the piping system, like frictions, obstructions, head loss, for example. So we can expect that the one that mechanical energy that's really living usually be like a little bit less. This one is not necessary. For special case like flow is incompressible and there is no losses, we will eventually regain the Bernoulli equation if we eliminate all the terms that are negligible, such as head loss and head pump and head turbine, and there is no mechanical work. So whatever that we obtain here, we obtain the Bernoulli equations back. So yeah, so that's why you see that this is the generic and more general equations that where it can be applied to many applications. Meanwhile, for the Bernoulli, as we know, Bernoulli equations is an ideal equations where we cannot consider the frictions or any irreversible losses or any shaft work in order to use Bernoulli equations. Okay. It is an ideal case equations. Kinetic energy correction factor alpha is used to remove the error which caused by the obtained kinetic energy from V squared over 2 is not the same as actual kinetic energy. So if alpha is not given in the problem, we can always assume it equals to unity or equals to 1. So you just need to add another terms into the one that we've seen before, the generic equations one. Just add with alpha, which is the correction factor. So this is in terms of power, rate of energy, and this is in terms of heat. So the same things, just add alpha in the kinetic terms. Okay, in this example, we have a pump which is pumping water from a lower regions to a higher place, where it is powered by a 15 kilowatt electric motor. Okay, so the power of this motor is 15 kilowatt, but the efficiency is only 90%. So the water flow rate through the pump is 50 liter per second, and the diameter of the inlet and outlet pipes are the same. So the diameter and the area is the same. So then plus the elevation difference across the pump is negligible. So the difference in height is not really significant. So if the absolute pressure at the inlet and outlet of the pump are measured to be 100 kilopascal and 300 kilopascal respectively, determine the mechanical efficiency of the pump and the temperature rise of water as it flows to the pump due to mechanical inefficiencies. So here, when we want to talk about this power or the rate of change in energies that I mentioned, first thing we need to find is the mass flow rates, because eventually you need to multiply mass flow rates with all the energy that we obtain from using the equations. So mass flow rates is the density of water 1 kilogram per liter and multiply with the volumetric flow rates. In this case, it's not really mentioned whether that this flow is incompressible or compressible, but since we are dealing with water or liquid, you can assume it's incompressible. So the volume that's in and out is the same. So the mass flow rate is same for the whole of this pump before and after. 50 kilograms per second, and then we know that the motor draws 15 kilowatt of power and only 90% is converted into the pump shaft work. So this is the total energy which is being supplied by this motor, and this is the efficiency which is converted into the shaft work. So the shaft work only receive 13.5 kilowatt, and then we need to find the mechanical efficiency actually. So what we need to know, so we are converting mechanical energy, which is or shaft work, into fluid by using pump. So it asks for the efficiency of the pump is equals to the energy of the fluid divided by the energy or work shaft or shaft work. So energy in the fluid divided by the shaft work, W pump. This is the things that we are looking for. Okay, so W pump is already known. So now we just need to find the rate of change of mechanical fluid in. So by using the equations, mechanical energy, total mechanical energy, and just by substituting this all, like we already know that P1 and P2 is already given. P1 is 100 kilopascal and P2 is 300 kilopascal, and the velocity should be the same. When for this case alpha is not given, alpha we can just assume it's equals to 1. B2 and B1 is the same, where we eliminate each other, and the elevation is negligible. I mean that you cancel each other as well. So what we have is only as a function of pressure. And then by substituting P2, P1 and the density of water and the mass flow rates, we get the fluid energy. And then we can find the efficiency of the pump, which is the output of pump is the mechanical fluid energy, and the input is the shaft work. So we have this 10 kilowatts over the shaft work, which is 30.5 kilowatt, which is the 90% out of the work done by motor. So it's only 74.1%. Okay, so if it asks what is the efficiency from the electric to fluid, for example, so like it's asked for motor pump. So what we need to do is just multiplying 74.1% and 90%. This will give you the overall efficiency. Just multiply these two. Okay, so in the second question, it asks how much temperature increases. Okay, this is not really related to fluid mechanics. This is more into heat transfer or thermofluid or thermodynamics. So basically, we know that this 74.1%, you can notice that you see the difference is 3.5 kilowatts different, and this inefficiency usually is due to the loss in terms of heat. It changed into heat. So we know that the amount of mechanical energy loss that is transferred into heat is equals to 3.5, which is the difference between 13.5 kilowatt and 10 kilowatt. And by using equation m dot c theta, the rate of the change of in temperature and the heat capacity of the water, this is the C. So from there you can find the change, and you can find the change in temperature in water, which is very small, 0.017 degrees Celsius. Okay, this is an example when you have hydroelectric power generations from a dam, and we have 2 points, 1 and 2. As usual, and this by using these generic equations, we include all these pump and turbine and head loss as well into these equations. And as we know that in this problem, we have no pump, this only turbine, and we might have some head loss. So usually head loss will be mentioned, and it's also here is mentioned that head loss is 35 meter. And so we know that pressure in these 2 points are the same. There are atmospheric pressure, and the velocity is negligible because the huge cross-sectional area, and the height is 120 meter, which is the difference between Z1 and Z2. And so basically the energy that's being extracted by the turbine is mainly due to the difference in elevations, and there will be some energies, have some reduction due to the head loss. And as we know, this is only the head, so when we want to change into energy, we multiply with gravitational accelerations, and this is it will give you the energy. So if you want to get the power or rate of work, you need to multiply with the m dot g HL. So that's why we have it's not L, it's turbine. My bad. It's when you want to convert from head to energy, which is a mass energy per unit mass, and then we want to change into the rate of work, multiply with the mass flow rates, we get the rate of work. And from the turbine to electric, you just multiply with the efficiency from turbine to electricity, which is 80% in this case. We get the amount of power is being generated into electricity. I guess that's all for chapter 5. We will continue. We get into chapter 6, inshallah. Thank you.